Right now, you are falling through a hole in space. Not a black hole, not some distant rift in the cosmos, but a void so massive it surrounds us completely. It stretches billions of light years across, yet somehow we never noticed. Inside this cosmic desert, galaxies drift farther apart, light bends in unexpected ways, and our very measurements of reality begin to warp. Because if what scientists have found is true, then everything we know about our place in the universe might be wrong. Before we dive into how that's even possible, take a second to get comfortable, because this story goes deep. If you're ready to see how we might be living inside one of the largest structures ever discovered, make sure you're watching closely. It all started back in 2013, when three astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, were mapping galaxies across the universe. They gathered data from tens of thousands of galaxies, expecting to find the familiar cosmic web, filaments, clusters, and vast spaces in between. But no matter which direction they looked, something was missing. There were fewer galaxies everywhere. About 20% fewer to be exact, spread across a region nearly 2 billion light-years wide, centered right around us. They double-checked their math, compared multiple surveys, and ran the numbers again. Each time, the result was the same. Our Milky Way seemed to sit inside a massive underdense region, a bubble of space where galaxies are scarcer and emptiness reigns. They had discovered what's now known as the KBC Void. When you hear the word void, you might imagine pure nothingness. A vast black emptiness with absolutely no matter inside. But in reality, a cosmic void isn't truly empty. It's more like the quiet valley between mountains or the holes in a piece of Swiss cheese. There's still matter there, just far less than average. Instead of 10 galaxies, you might only find 1 or 2 scattered across the same volume of space. The rest is filled with diffuse gas, faint traces of dark matter, and of course, dark energy quietly pushing everything apart. Across the universe, these voids weave together with galaxy clusters and filaments to form the grand cosmic web, the universe's largest structure, and the space between those threads, that's where the voids live. But here's the part that changes everything. The one we're in isn't just any void, it's enormous. Billions of light years across, making it one of the largest ever identified, which means if we truly are sitting inside it, the entire way we observe the universe could be slightly distorted. Distances might look different. Light could appear to stretch in ways we didn't expect. Even our measurements of the universe's expansion might be off. Because if space itself is thinner around us, then everything we see beyond this bubble could be tricking our instruments, just a little. And that little might explain one of the biggest mysteries in cosmology. To understand why this matters, we have to talk about a problem that's been haunting astronomers for years: the Hubble tension. It's the growing disagreement between two ways of measuring how fast the universe is expanding. One method looks at the early universe, using the faint glow of the cosmic microwave background, the leftover light from the Big Bang. It suggests an expansion rate of about 67 kilometers per second per megaparsec. But when we measure the expansion nearby, using supernovae and variable stars, we get a higher number, closer to 73. That may not sound like much, But in cosmology, it's a massive difference, one that could rewrite the laws of physics. So, what's going on? Well, if we're living inside a giant underdense bubble, like the KBC Void, that could be part of the answer. Inside a void, matter is thinner, gravity is weaker, and space expands just a little faster than average. So if we're measuring the expansion from within that bubble, it would look like the universe is stretching more rapidly than it actually is. That could explain why our local measurements keep coming out higher. It's not that the cosmos is lying to us, it's that we might be standing in the one spot where space itself is skewing our perception. And if that's true, the Hubble tension might not be a mystery after all. It might just be the first clue that we've been living inside a cosmic hole all along. To understand how a void can change our view of the universe, you need to picture what's really happening inside it. Even though it's emptier than average, a void isn't some region where gravity stops working. It's the opposite. Gravity from the denser walls around the void still pulls everything toward them. That means galaxies inside a void, including ours, are constantly being tugged outward, away from the center, toward the edges, where matter is thicker. It's like standing in a shallow valley surrounded by mountains. Gravity is always pulling you uphill, no matter which way you turn. Over billions of years, this pull causes voids to expand faster than the rest of the universe. Galaxies at their edges appear to drift outward, and the space inside keeps stretching and thinning. If you could watch it in time-lapse, you'd see clusters on the edges getting denser, while the middle grows darker and more silent. Astronomers can even measure this motion. Our own Milky Way, for example, is moving at nearly 600,000 miles per hour, partly because of the push from nearby voids and the pull from denser regions beyond. This combination of outward flow and gravitational attraction makes the local universe incredibly dynamic. A constant tug-of-war between emptiness and matter. And that subtle motion, the way light travels through this distorted landscape, can bend our measurements just enough to make the cosmos look different depending on where we stand. So when we measure the universe's expansion, we're not just seeing the universe as it is, we're seeing it through the lens of the bubble we live in. Zoom out, and you start to see the bigger picture. The universe isn't evenly filled with galaxies. Instead, it's arranged like a vast, three-dimensional web. A network of filaments, clusters, and immense empty regions in between. These patterns began as tiny ripples in the early universe, seeded by quantum fluctuations just fractions of a second after the Big Bang. Over billions of years, gravity pulled matter toward the denser regions, forming walls and knots of galaxies, while the emptier regions, the voids, kept expanding. Today, those voids make up nearly 90% of the universe's volume, even though they contain only a small fraction of its mass. From a cosmic perspective, most of existence is made of emptiness, threaded by narrow veins of light. And somewhere within that web, between the glowing filaments and the dark, expanding hollows, sits us. Our Milky Way rests on the edge of one of those colossal empty regions, the KBC Void, quietly floating in the vast gulf between cosmic walls. It's a haunting thought that most of the universe isn't galaxies or stars or even dark matter. It's space. Endless, silent space, stretching far beyond what our eyes can see, shaping everything we measure, everything we believe, and maybe even the story we tell about how the universe came to be. So where exactly are we in all this? According to the data, our Milky Way isn't right at the center of this vast bubble. But we're not far off either. We sit roughly a few 100 million light-years from the middle of the KBC Void, still deep within its boundaries. Surrounding us is a sprawling collection of galaxies called the Laniakea supercluster, home to over 100,000 galaxies stretched across more than 500 million light-years. And yet, all of it, every cluster, every filament, every glowing galaxy, still lies inside this enormous underdense region. It's a strange paradox. We live in what seems like a massive supercluster of galaxies that's also floating inside a cosmic desert. Our entire neighborhood, the Virgo cluster, the Great Attractor, and the filaments that connect them, is part of this delicate structure, balanced between emptiness and gravity. Just beyond it, the density of the universe begins to rise again, like the outer walls of a bubble thickening after the thin, transparent interior. Some researchers suggest our position could even explain why the universe appears to move in certain directions. Our Milky Way, for instance, is hurtling through space at hundreds of thousands of miles per hour. Motion partly caused by the pull of denser regions beyond the void and the gentle push from the emptiness behind us. We're drifting along the flow of the cosmic web, caught in a current that spans billions of light years. It's humbling to think about. Everything we've ever known, every star, every planet, every trace of life, is moving together through a near-infinite hollow in the fabric of the universe. And until recently, we had no idea. But extraordinary claims need extraordinary evidence, and astronomers didn't stop at one survey. They went searching for proof from every possible angle, and what they found only deepened the mystery. First, they looked at the large-scale structure of the universe using something called baryon acoustic oscillations, ripples left over from sound waves that traveled through the early cosmos. These ripples act like a cosmic ruler, letting scientists measure how galaxies are spaced at different distances. When they compared local measurements to faraway ones, the local region, our region, appeared slightly underdense, matching the predictions of a void. Then they turned to the cosmic microwave background, the faint afterglow of the Big Bang. When light from that background passes through a void, it loses a bit of energy, creating a tiny cold spot in the sky. And sure enough, astronomers have detected one, a region colder than it should be, aligned suspiciously close to our position in the universe. It's as if light itself is whispering the outline of the bubble we live in. Finally, they studied galaxy flows, the motions of entire clusters drifting through space. Instead of random movement, astronomers found a large-scale flow, hundreds of millions of light-years across, where galaxies appear to be moving outward, away from a central region of low density. In other words, the universe around us behaves exactly like what you'd expect if we were inside a giant void. Each observation on its own might be coincidence, but together they paint a consistent, unsettling picture. Everywhere we look, from the nearest galaxies to the edge of the observable universe, the data keeps pointing to the same conclusion. We're living in a cosmic hollow, one so vast and subtle that it's bending the very way we measure the universe itself. Of course, not everyone is convinced, because if the KBC Void really is as large as it seems, then we've stumbled into something cosmologists never expected. Something the standard model of the universe struggles to explain. According to current simulations, voids this big should be incredibly rare, so rare that the odds of us living inside one are practically zero. That leaves scientists with two uncomfortable possibilities. Either we've just gotten unimaginably lucky, the cosmic equivalent of finding ourselves living inside the one bubble in a trillion, or our understanding of the universe itself is incomplete. If it's just luck, then fine. But if it's not, if this void is real and common enough to exist under the laws of nature, then the physics we've trusted for decades might be missing something fundamental. Maybe our models of how structure formed after the Big Bang aren't perfect. Maybe gravity doesn't behave exactly the way we think it does on the largest scales. Or maybe the early universe had different conditions, subtle variations that made certain regions like ours expand faster and thin out more than others. It's a mystery that touches the very foundations of cosmology. Because if the cosmos isn't uniform, if we really do live in a special place, then the cosmological principle, the idea that the universe looks the same everywhere, might not hold true, and that would rewrite everything. So, what could possibly create a void this enormous? Some physicists have looked toward modified gravity, theories that tweak Einstein's equations just enough to make underdense regions grow faster and larger than expected. One idea, known as MOND, short for modified Newtonian dynamics, changes how gravity behaves at very low accelerations. It was originally designed to explain galaxy rotation without dark matter, but it also predicts that cosmic voids could become much deeper and wider than in standard models. The catch? While MOND can make our local universe fit the data, it struggles to explain other observations, like the detailed patterns in the cosmic microwave background, or how light bends around massive clusters through gravitational lensing. Every theory that solves one problem seems to create another. Others argue that the void might not require new physics at all. Maybe it's just a statistical fluke, a rare but possible arrangement of galaxies that happen to form around us. Or maybe some say the tension in the data comes from our measurements, tiny systematic errors in how we measure supernova distances, or how dust and calibration affect brightness. Yet, despite years of refinement, the disagreement persists. The Hubble tension hasn't gone away. If anything, it's only grown sharper. So, we're left balancing on a knife's edge between coincidence and revolution. Either we're in a strange but ordinary patch of space, or we're staring at the first sign that our universe doesn't work the way we thought. If we are inside a vast cosmic hole, the implications ripple outward far beyond just galaxy counts or expansion rates. A faster local expansion would mean the universe around us appears younger than it really is. If the higher, local Hubble rate were the true one, the age of the universe would shrink by over 1 billion years, making some of the oldest known stars suddenly older than the cosmos itself. That doesn't make sense, unless the expansion rate really does change depending on where you are. And that idea, that the universe's properties might not be perfectly uniform, threatens the foundation of modern cosmology. Everything from dark energy to the age of time itself depends on that assumption of sameness. If it breaks, our entire model of the universe might need rebuilding. Even the mysterious dark energy, the force accelerating the expansion, could be behaving differently inside the void. Perhaps it's slightly stronger here, where matter is thin and space has room to stretch. If so, we could be living in a natural laboratory, a place where dark energy's true nature is easier to observe. Future surveys, from telescopes like Euclid, DESI, and the Vera Rubin Observatory, are being designed to test that very idea. They'll peer deeper into space, looking for more voids like ours, and map the fabric of the cosmos with unprecedented precision. Because if it turns out we really are inside a giant underdense bubble, then our view of the universe isn't just unique. It's distorted, magnified, and shaped by the very emptiness that surrounds us. And understanding that emptiness might be the key to finally understanding everything. But maybe this isn't a curse. Maybe it's an opportunity. Because if we really do live inside one of the largest voids in the observable universe, then we're sitting in the perfect natural laboratory to study how the cosmos works. Inside a void, the effects of dark energy become more visible. There's less gravity to fight against it, so space itself can stretch more freely, revealing the true behavior of the mysterious force driving the universe's acceleration. Astronomers can watch how galaxies drift and how the void's edges evolve to measure dark energy's strength and consistency. They can test whether it's truly constant or if it changes from one region of space to another. Even the shapes and growth rates of smaller voids can help confirm whether our current model of the universe, called lambda CDM, still holds up. New surveys from the Euclid Space Telescope, the Dark Energy Spectroscopic Instrument, and the Rubin Observatory are now mapping millions of galaxies, hoping to trace these cosmic hollows in detail. If they find other regions like ours, it could confirm that giant voids are not rare accidents, but a fundamental part of how the universe organizes itself. So rather than a strange coincidence, our location might actually be a gift, a quiet corner of the cosmos that lets us peer into the deepest mysteries of existence. Life inside a void looks very different from the busy filaments that span the cosmic web. The galaxies that do exist here are lonelier, smaller, dimmer, and more isolated. They tend to be gas-rich spirals or irregulars, quietly forming stars far from the gravitational chaos of clusters. With fewer nearby galaxies to interact with, their evolution slows down. They grow more gradually, undisturbed by the violent mergers and collisions that shape denser parts of the universe. But this isolation can have surprising effects. Some void galaxies are unexpectedly active, using their abundant gas to ignite bursts of new stars. Others show unique chemical fingerprints, holding less heavy metal content than typical galaxies, yet not as little as theory predicts. It's as if they've evolved on their own terms, untouched by the constant recycling of matter that happens in the crowded parts of space. If you could stand inside one of these galaxies and look out, the sky would feel emptier. Fewer points of light, fewer neighboring clusters, more darkness. It would be the ultimate sense of cosmic solitude. A galaxy adrift in the quiet backwaters of creation. And then comes the question we can't help but ask, what if someone else lives out here too? If a civilization were born inside a void, their entire view of the universe would be different. Their night sky would hold fewer galaxies, and the nearest clusters might lie billions of light years away. Their measurements of cosmic expansion would tell them that the universe is stretching faster than it really is. They might believe they lived in an unusually energetic cosmos, one younger, smaller, and more rapidly expanding than ours appears to be. In a way, that's exactly what's happening to us. Our perspective is shaped by where we happen to be, by the invisible landscape of density and emptiness that surrounds us. Maybe every intelligent species looks out at the universe and sees something slightly different, their observations bent by their own cosmic neighborhood. It's a humbling thought that even the truths we think are universal might depend on where we stand. And if we ever do meet another civilization, perhaps one living in a dense cluster or another void entirely, we might realize that their universe and ours, though made of the same stars, aren't quite the same at all. You've just scratched the surface. Tap subscribe and let's keep chasing the questions that make the world so strange and fascinating.